In section 2.3, we're going to introduce acceleration, which can be a little bit trickier. So let's just give it a shot and you guys let me know if you get stuck. So, an acceleration happens whenever the velocity changes. That's the definition of an acceleration, is the rate of change of your velocity. But the direction of the acceleration can be quite tricky. So here's my suggestion, in parentheses here. Changing the velocity is going to require a force. And the acceleration's direction is the same as that force that would be needed. So let's imagine maybe a cart on a track, and this can be its original position with its original velocity, 1 meter per second to the right, or you could have also said in the positive x direction. And then sometime later, finally, it's over here now, and it's moving faster at 3 meters per second to the right. So if a cart was just on a flat track and it was slower and then faster, doesn't it seem like something like somebody's hand had to push on it in this direction to get it to go faster? So the force needed to speed it up would be to the right. And if the force needed to speed it up is to the right, then the direction of the acceleration must be to the right. So let me just take a second here and make a little catalog of things. My initial velocity, I would say, is in the positive direction. My final velocity is also going to be pointing in the positive direction. The force is pointing in the positive direction, and the acceleration is pointing in the positive direction. And the overall result is that it speeds up. All right, new example. Again, I've got my plus x defined to be to the right. So originally it's moving to the right at 3 meters per second, and sometime later, finally, it's moving slower to the right at 0.5 meters per second. So if a cart was moving forwards and it has to slow down, you can almost imagine somebody's hand kind of getting in the way and pushing on it to slow it down. You have to imagine like the hand pushing backwards on the cart. So the force needed to slow it down is actually in the backwards direction, or we could say in this case the negative direction. To slow it down here, you need the force to be working against the direction of motion. If the force is to the left, then the direction of the acceleration must be to the left. Finish our little catalog here. Original velocity was positive to the right. Final velocity was positive to the right. Right, the force to cause that change was left or negative direction. And the acceleration then would also be left or negative direction. The result is that the cart slowed down. So far this isn't too bad in that a positive acceleration sped it up and a negative acceleration slowed it down, but this next example might not be intuitive. So let's say originally my object was moving to the left, but I'm still going to say that my positive x direction is to the right. So it's going to start off with a negative speed. Let's say 1 meter per second. And then sometime later, it's over here at a final position, and it's moving left faster, let's say at 5 meters per second to the left. So in that case, it's going to speed up. And it's going to speed up to the left. So it's almost like you have to imagine somebody pushing on the cart, kind of helping it in the direction of motion, push, 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 to get it to go faster. So the force that I'm imagining right now is pointing to the left, which also means that the acceleration is to the left. All of these arrows are pointing to the left. So by my coordinate system that I defined here, all of these arrows are in the negative direction. So here, a negative acceleration actually sped it up. So if this plays with your head a little bit, let me just rephrase it this way. If the velocity and the acceleration, which you could also say the force, right? If they're in the same direction, it will speed up. If the velocity and the acceleration are in opposite directions, it will slow down. The acceleration can be measured. It does have a value. And in order to find the average acceleration, we would find the change in velocity between an initial time and a final time, and divide it by the change in time that it took to do that change in velocity. So this is our equation right here to find the average acceleration. Your book gives you an abbreviation. A here is the acceleration. Again, that little bar over it just means average, so we have the average acceleration. And the average acceleration is usually going to be in units of meters per second divided by a second. And while this is true, and I won't ever dock you for it, traditionally we just write it this way, meters per second squared. They're both fine. Okay. Just make sure that your acceleration has units of a length over time squared, because otherwise it's not an acceleration. Right. In order to find that, you have to take the final velocity and subtract the original velocity, and then divide it by the time interval between the original time and the final time. As a quick example, I made this up. A car was going east at 20 meters per second. After 20 seconds, it is going 10 meters per second westward. What was its average acceleration? And if you ever are asked for an acceleration, you should make sure to remember that it's a vector and you should give a direction. So I made a little figure where I sketched it originally moving 20 meters per second eastward or rightward. And then at some other point it would stop and turn around and be going backwards, so it'll be going west or left at 10 meters per second. I'm going to say that my positive direction is going to be to the right, which is just typical but is not necessary. So let me show you something real quick that I can notice from this figure. Here it's going to be 20 meters per second to the right, and then somewhere right over here at the edge here it's going to stop for an instant, kind of while it's turning around. So this whole time it's going to be slowing down. So the velocity is to the right, but it is slowing, so that the acceleration has to be opposite of this direction. The acceleration is to the left. And then from this point, right after it stopped to turn around, it was speeding up to go to the left so it could reach 10 meters per second leftwards. And in that case it's speeding up, so V and A arrows must be aligned. The velocity was to the left, so the acceleration must also be to the left in order for it to speed up. Here I said that my initial velocity, but you could have also said original velocity. It's fine, whatever. These little subscripts are basically notes to yourself. It was equal to 20 meters per second eastward, which I'm just going to use as positive 20 meters per second when I plug it in for math. My final velocity was 10 meters per second to the west, but if I'm going to plug it in for math, instead of saying west, I'm just going to say negative to mean the negative direction. So negative 10 meters per second. So then I grabbed the acceleration equation, nice and abbreviated, nice and short, but let me just read through it real quick. The average acceleration is going to be equal to the final velocity minus the original velocity divided by the time interval. So the final velocity was negative 10, so we plug it in, minus the original velocity, which was positive 20, we plug it in, divided by the time taken, 20 seconds. So we end up with negative 30 meters per second divided by 20 seconds. Doing the math here, I get negative 1.5. And the units, I'm just going to carry them through for a second. But we could play with this fraction here and rewrite it this way, as a meter divided by a second times second. But then, tradition, we would just actually rephrase the units one more time here just to say meters per second squared. Right, so in the future I'm probably going to skip from this to this pretty fast. A meter per second divided by a second, it can be rewritten as a meter per second squared. Our average acceleration came out to be negative, and that is fine because that is our direction. The acceleration was west. For final answer, I'll round it to 1 sig fig, make sure I've got the right units on there, and it was a vector, so I have a direction.